So let's continue our exploration of continuous random variables and their PDFs. In particular, I'm going to give you an example of one of a continuous random variable, and we're going to check if the functional form that you're provided with is actually a probability density function. So I am talking about an exponential distribution. It has the form of f of x is equal to 1/3 times e to the power of minus x over 3 for non-negative values of x and 0 otherwise. So the question that is being posed here is this actually a PDF, a probability density function? So it does have to meet two properties that we have already discussed. The first one being non-negative, and actually we can verify, we know what this form looks like, the negative exponential. If you think e to the x is it's a function that increases at an increasing rate. So this is e to the power of x and e to the power of minus x from your sort of basic understanding of functions is declining for the domain of x. And in this format where there's no parameter in front of the x, it passes through the value of 1 on the y-axis. It never reaches 0. So the f of x actually approaches 0 but never reaches it. So we can claim from the diagram and from the graphical representation here that this is a non-negative function. That's great. The property that we want to work a little bit more on is the second property that involves calculating the integral from minus infinity to infinity and see if we actually get to a value equal to 1 once we've processed that integral. So what do we do here? For minus infinity, you can break this into two parts, for minus infinity to 0 and from 0 to infinity. So the functional form takes the value of 0 for these x values where this integral ranges. So integral of 0 dx, that's going to give us 0. And essentially this is the integral that we need to calculate for the domain of the x values that we care about. If you would like to practice how to solve this, you can pause the video now and see if you remember how you do this calculation. How do you do this integration? How do you prove that this quantity is actually equal to 0? But if you don't remember, you can follow my guidance as we progress in solving this particular problem. So essentially this is what we're left with, because this quantity is equal to 0, so this transfers over and we're going to try to find a solution here. So one of the things that we need to realize is that we can't work with sort of this infinity symbol over here. We need to translate that into a value, and we're going to write this value being, let's say, b, with exploring the limit of b approaching infinity. So the structure of limits is important for our understanding, obviously, of calculus and derivatives and integration. But in this particular case, we are going to use it in order to find a solution here. So what's going to happen, or what is happening in this particular case? Well, we can't work, we're going to try to reduce this into a form that we can work with. So we have some good understanding of how to integrate a form of e to the power of x, but this is a little bit different, so we need to modify this form, and we do that by saying, let's say we make this a variable, and let's call that v. So v is going to be equal to all of this, the minus x over 3. Okay, so I wrote that here. Once you do, then you can sort of figure a few other things out, right? So you can apply the rules for differentials, and you can say, well, now dv is going to be minus 1/3 dx. You could simply try to calculate the derivative of v with respect to x, and you find exactly the same thing. So we're going to use this information over here in the form of the differential, and we're going to do some substitutions, right? So I'm going to substitute v over here. I'm going to substitute this 1/3 times dx that remains away. We have an expression here. It's very close to this. So here's what's happening. E to the v, so simply with this substitution, dv, how did dv come here? So we know that dv is minus 1/3 times dx. We have 1/3 times dx over here. We just need the minus sign. So we put that minus sign outside of the integral. It doesn't really matter. And then we substitute these two things in here as dv. That's great. The other two things that we care about is the endpoints. of the integral. So this integral is expressed in terms of variations in x. Now we need to express it in terms of variations in v, this new variable that we developed. So this transformation essentially of x. So the endpoint here, so if x is 0, what is going to be the value of v? If x is 0, minus 0 over 3, that's 0. So we substitute it over here. If x is equal to b, right? So minus b over 3 is going to be the value for variable v, right? So minus b over 3, that's going to be the upper point for the integral. So now we are in a format that we know how to serve the integration problem for. How do you do this? So this is going to be minus e to the power of v, so you substitute minus b over 3 over here, minus all of this raised to the power of 0. So this is what's happening here, and of course you have to close all of the parentheses that you open. So we saw application, we saw the theory behind the exponential distribution. Let's look at a practical example. We're going to a little bit about you can model a real situation of customers entering a store, let's say supermarket, and model the process of checkout for that particular place. So what the exponential distribution describes, the arrival time or a time completion, both of these would be valid, of a randomly recurring independent event sequence, right? So customers approach a cashier waiting to sort of be checked out is one of those things that you could consider as a randomly recurring independent event sequence. Now, there would be some discussions to have about how independent occurrences or these events are, but assume that for the time being that they are independent. It has been an important or function for about science, engineering, and business. It has been used quite a bit in what we call queuing theory. That is quite also important for things like the internet, where sort of data packages arrive at servers and they leave servers, and sort of the modeling of that process. If this theta is a parameter that is capturing, let's say, the mean waiting time for the next event recurrence, we can write the PDF in the format you have seen. Okay, the f of x, in this particular case we add this general parameter here of theta, is equal to 1 over theta times e to the minus x over theta, for x being greater or equal than 0, and 0, the value of the f is 0 otherwise. Diagrammatically, you have seen how the exponential looks. This is the case where theta is equal to 1. So how do we use it? With a given theta, right, is the data that we might be collecting from a supermarket about what is the mean waiting time for the next event recurrence. That essentially means, on average, how much do you have to wait before you get cashier actually start to check you out from the moment that you sort of join the queue. If that is the theta value is equal to 3, you can automatically define the 1 over theta over here, right? So that's going to be 1 over 3, and then this is going to be minus x over 3. What is this 1 over theta conceptually? This is essentially a processing rate, right? So how many people a cashier per minute in this particular case. It's not even a full person per minute. It's about a third of a customer per minute. So you have all of this information. How can you extract? Can you extract some sense of a probability for this example? What would that probability be looking like? So given that is 3, you could ask this question of what would be the probability of checking out in less than 2 minutes. Okay, so in this axis, essentially, you would say this is 1 minute, this is 2 minutes, 3 minutes, and you can go on and sort of continue this axis. So essentially, you would say, well, what is the probability that you're going to be in this space, like getting sort of out in less than 2 minutes? So what we've said before is that in this continuous random variable case, the height of the function the probability density function, is not going to give you a probability value over here. Simply going to give you sort of this idea of density. What you do get the probability value is by calculating the area underneath curve, right? And up from the point from 0 up to second minute. We don't know how to do this calculation yet, but you can already understand that this is going to involve integrating this functional form from 0 to 2, because that's how we extract areas under a curve. We will up this problem when we talk about distribution functions. You can also use packages, extract these types of probabilities without sort of having to solve these problems analytically. So in particular, here you can see a little bit of sort of handwritten code if you went into a software programming language like R, sort of how you would be getting an answer to the problem that was. But we will solve this problem, the actual functions, and solve it sort of our understanding of integration. So another point that's worthwhile to make is that if this f function is the PDF of x, then we can calculate probabilities for events like x falls within alpha or a and b. How do we do that? We simply integrate that functional form with these two endpoints applied to integral, and that's going to give us the probability that we are so for the function that we have already seen in the format that we have seen it, we know it's a PDF. We're asked to the probability that falls within the values of 0 and 3. So how are we going to do that? We simply apply the definition of how we calculate these probabilities. So essentially we apply these endpoints to the integral. We can use the same exact for calculating, reformulating this problem where minus x over 3 has its own variable, right? So here I called it u. You can calculate du over dx. You can sort of redesign the endpoints, right? So if u is equal to minus x over 3, when x is equal to 0, this is going to be 0. When x is equal to 3, this is going to be minus 1. So essentially you can apply this transformation over here. I forgot a du in this expression. Okay. When you solve for this integral, you're going to get in the standard format of e to the power of u. Going to get that this is equal to 1. That's going to be a plus 1, so it's 1 minus this expression over here, which you can make a sort of a calculation, figure out exactly what the numeric value of e to the minus 1 is, and get to the answer. So you use your trusted calculator or a software platform for mathematical or statistical programming, and you can extract the probability. So we calculate it. But at 632 or 63 point. So a couple of additional to consider here. You have x being a continuous random variable with a PDF that you express as f of x, lowercase f. Then, worthwhile also noting from our understanding of integration, the probability of x receiving a particular value based on the way that we have defined probability distribution function would essentially signify that you're calculating an integral a to a of the functional form f of x dx. By definition is equal to 0. A intuitively is a very, very specific number in sort of sequence of real numbers to assign a positive probability for. We cannot expect that x is going to be exactly 2, right? A number that is quite specific when it could have been 2.000001. So it depends on sort of granularity of how you're measuring each of these variables. So any continuous random variable can expect the following equivalencies. So essentially when you have a strict inequality or an equal, doesn't really matter. It's not going to affect. The boundaries are not going to play a role in terms of adding probability or subtracting probability. So all of these expressions are going to be giving us the same in terms of calculating probability. So this node opens up the possibility that the PDFs of X are not of a random variable X are not unique. So because you can start introducing some discontinuities, eventually are not going to play a role in these probabilities. So notice in this case, have the example that we have been working with. Value of the f of x at x is equal to 0 is 1 over 3. Let's say we make a variation of this, and we here open, and we give a value of the PD 1 when x is equal to 0, and then the rest of the functional form remains the same. On the basis of this understanding that we cannot assign a positive probability for any specific point, any specific value of x, means that there's an infinite number of PDFs of X that look like this but have a form of discontinuity, and you can take advantage of that fact when you're modeling a variety of processes. This point gives rise to a third case of the types of distributions that you can have. There is the idea of a mixed distribution. These are random variables, have characteristics of a continuous random variables for a portion of the distribution, the domain of X, and random variable characteristics for another part of the domain. So an example here would be, say, the length of time in hours, in thousands of hours, that a computer or a laptop operates properly. We call that, so you could very well say that the probability that x is equal to 0, at a specific point in the domain of x, is 1/4. That is a very high probability in this example that a laptop screen is not going to operate properly the moment you try to turn it on, at time 0 essentially. And then the rest of the probability distribution follows the exponential that we have, or a form of the exponential that we have. That be an example of a mixed distribution that would be seeing in probability and statistics.